A pressure relief valve can be correctly sized, properly certified, installed on the right vessel, and still fail as a protection system. That is the uncomfortable truth behind API 520, and it is where serious engineering begins. You are not designing a valve. You are designing an emergency pressure release path that must work during the worst credible event after years of operation under real process conditions, with real piping losses, real back pressure, real fouling, real maintenance constraints, and real human intervention. That distinction changes everything. The first question is not, what valve size do I need? The first question is, what can actually cause this equipment to overpressure? A blocked outlet, control valve failure, utility loss, exchanger tube rupture, external fire, thermal expansion, gas blowby, compressor failure, loss of cooling, uncontrolled reaction, or steam breakthrough can each create a different relieving load, temperature, pressure, fluid phase, and duration. If the scenario is wrong, the calculation is wrong. It does not matter how accurate the equation looks or how polished the datasheet appears. You must separate two engineering problems clearly. First, determine how much fluid must be relieved. Second, determine what device and flow area can safely relieve it. The first is process system analysis. The second is relief device engineering. A perfect valve sizing calculation cannot rescue a badly defined overpressure case. You also need to control the pressure language, because pressure relief design becomes confused when operating pressure, design pressure, maximum allowable working pressure, set pressure, overpressure, accumulation, and relieving pressure are treated as interchangeable values. Maximum operating pressure belongs to normal operation. Design pressure belongs to the mechanical design basis. Maximum allowable working pressure represents the actual permissible pressure capability of the completed equipment at the relevant temperature. Set pressure is where the relief device is adjusted to open. Overpressure is the increase above set pressure used to achieve relieving capacity. Accumulation is the increase above the equipment's maximum allowable working pressure during the event. Relieving pressure is generally set pressure plus permitted overpressure. The practical rule is simple. Do not size at normal operating conditions. Size at relieving conditions. Relieving temperature may be much higher or lower than the normal process temperature. That change can affect density, molecular weight basis, compressibility, flashing, viscosity, vapor fraction, and required flow area. When you carry normal operating data directly into a relief calculation without understanding the actual upset, you are not simplifying engineering. You are hiding uncertainty. You must also understand what a pressure relief device can and cannot do. It protects against overpressure. It does not protect against every failure. It cannot repair lost wall thickness, prevent brittle fracture, overcome blocked discharge piping, compensate for a closed isolation valve, restore material strength during prolonged fire exposure, or correct an incorrect process scenario. It will not save equipment from every structural, thermal, chemical, or mechanical failure. A relief valve is a safeguard, not magic. Now consider the device itself. A conventional spring-loaded valve is simple, proven, and effective when the service suits it. Process pressure acts against spring force, the valve opens near set pressure, and it recloses after the pressure falls sufficiently. Its main weakness is back pressure sensitivity. If the outlet is connected to a flare or common relief header, you need to know the superimposed back pressure before the valve opens and the built-up back pressure created after flow begins. You need to know whether those values are constant, variable, or influenced by simultaneous relieving events elsewhere in the plant. A conventional valve may be completely acceptable in one system and completely wrong in another. You should never select it because it is the familiar default. Balanced bellows valves are used when back pressure could significantly influence a conventional valve. The bellows arrangement reduces the effect of outlet pressure on the moving assembly and can also help isolate internal components from corrosive service. But the bonnet vent is part of the functional design. If that vent is blocked, plugged, pressurized, or routed into an unsuitable system, the balancing function can be compromised. A balanced valve with a badly engineered bonnet vent is not a balanced installation. Pilot-operated valves offer another set of advantages. They can operate closer to set pressure, reduce leakage, handle large capacities, tolerate certain back pressure conditions, and use remote sensing. They can also fail when the surface is dirty, viscous, corrosive, polymerizing, freezing, or loaded with solids. Small pilot passages, sensing lines, seals, and control components can be vulnerable to plugging, hydrate formation, wax, contamination, and material incompatibility. More sophisticated does not automatically mean more reliable. Complexity must earn its place in the design. You also need to distinguish between pop action and modulating pilot operation. A pop action pilot drives the main valve rapidly toward full opening. A modulating pilot opens only as much as needed to satisfy the required flow. Neither is universally better. The correct choice depends on process dynamics, relieving demand, inlet pressure loss, valve stability, and interaction with the downstream header. Remote sensing also needs to be understood honestly. It can allow the pilot to sense true system pressure upstream of a restrictive inlet line, but it does not remove the restriction itself. The main valve still receives flow through the physical inlet path. Capacity can still be reduced, pulsations can still develop, cycling can still occur. Remote sensing can correct where pressure is measured. It cannot repeal fluid mechanics. Fluid phase is another area where weak assumptions create bad designs. Gas and vapor valves do not behave exactly like liquid service valves. Vapor expansion helps generate rapid opening forces. Liquids rely more on momentum and reactive forces. A valve designed for vapor service should not automatically be assumed suitable for liquid duty. A vessel containing liquid may relieve vapor. A heat exchanger may relieve liquid, vapor, or two-phase fluid depending on the failure mechanism. The correct question is not, what does the equipment normally contain? The correct question is, what reaches the relief device during the governing event? Two-phase flow deserves particular caution because it can invalidate simple gas-only or liquid-only assumptions. Flashing, changing vapor fraction, and uncertain phase distribution can materially affect device behavior and capacity. When phase behavior is uncertain, certainty in the final orifice size may be artificial. Now consider oversizing. Many engineers still believe that a larger relief valve is automatically safer. It is not. If the required relieving flow is far below the capacity of an oversized valve, the valve may open, rapidly depressurize the local inlet volume, close, experience pressure recovery, and reopen. That cycle can become chatter. Chatter can damage the seat, disc, spring, guide, bellows, piping, and nozzle. It can also reduce effective relieving capacity. The correct objective is not the largest possible valve. It is the smallest standard orifice that safely meets the required duty after all applicable corrections are applied. Good conservatism adds resilience. Bad conservatism creates another failure mode. Rupture discs create a different set of decisions. They are fast, simple, and have no moving parts, but they are non-reclosing devices. Once a rupture disc opens, the process remains connected to the discharge path until intervention occurs. You therefore need to think beyond burst pressure and consider product loss, shutdown implications, environmental release, flare loading, replacement access, detection, and isolation. A rupture disc is simple hardware. Its application is not simple. Burst pressure depends on disc temperature. The temperature at the disc when it bursts may not equal the vessel design temperature, normal operating temperature, or general process temperature. If the temperature basis is wrong, the disc may open at a pressure different from what you intended. Operating ratio matters as well. Different disc designs tolerate different relationships between normal operating pressure and marked burst pressure. Cyclic pressure, pulsation, vacuum, and pressure fluctuations can shorten life and cause premature failure. The real selection question is not only what burst pressure do I need, it is also how close will normal operation run to that pressure, and can this design survive the actual service? Forward-acting, reverse-acting, and graphite discs are not interchangeable. They differ in opening mechanism, operating ratio, pressure cycling capability, corrosion resistance, vacuum behavior, and fragmentation. Fragmentation becomes critical when the disc is installed upstream of a relief valve. A fragmenting disc can interfere with the downstream valve and turn a protective combination into a blockage risk. When a rupture disc is installed upstream of a relief valve, the space between them must be managed. If the disc leaks and pressure builds in that interspace, the differential pressure available to burst the disc is reduced. The vessel may then have to reach a higher pressure before the disc opens. That hidden pressure can silently defeat the intended protection basis. The interspace needs suitable venting, indication, monitoring, or telltale detection. Never allow an unmonitored trapped pressure zone between a rupture disc and a relief valve. Orientation and bolt torque are equally serious. A rupture disc installed backward may not burst at the intended pressure. Incorrect tightening can distort the disc or holder and change sealing or opening behavior. You should treat the disc as a calibrated, pressure-sensitive element, not as a passive piece of metal. Now move upstream to the inlet piping, where one of the most common failures begins. Excessive inlet pressure loss can destabilize a relief valve. The valve opens, flow increases, pressure at the valve inlet falls, the valve begins to close, pressure recovers, and the valve reopens. That rapid cycle is chatter. For many conventional installations, non-recoverable inlet pressure loss is normally controlled to a small fraction of set pressure, commonly around 3%, unless a justified engineering basis supports another arrangement. This is not a cosmetic design rule, it is a stability requirement. You reduce inlet loss by shortening the line, increasing diameter, removing unnecessary fittings, smoothing the entrance, reducing restrictions, and evaluating the line at the rated relieving capacity. When a rupture disc is installed upstream, its pressure loss must also be included. The inlet pipe should not be smaller than the valve inlet connection, but nominal size alone does not guarantee good performance. A same-size line can still be too long, too restrictive, or badly configured. Long inlet lines also create dead legs, trapped liquid, solids accumulation, corrosion pockets, and delayed pressure transmission. Relief inlets should be short, direct, and self-draining wherever practical. Avoid casually connecting process laterals to a relief valve inlet. Simultaneous process flow and relief flow can increase pressure loss and destabilize the valve. Where such a connection cannot be avoided, analyze the combined condition. Turbulence matters as well. A relief valve located immediately downstream of a control valve, pressure-reducing station, sharp elbow, T or high-velocity restriction may sense an unstable pressure field. Convenient layout is not always good hydraulic design. The outlet side can be just as decisive. Back pressure can determine valve type, available capacity, correction factors, and stability. The discharge system must be evaluated from the valve outlet through the tailpipe, fittings, subheader, main header, knockout vessel, and final disposal point. Do not check only the first few meters of pipe. The valve experiences the resistance of the complete connected system. Rapid depressurization can also produce severe cooling. Auto refrigeration may lower the temperature of the valve outlet, tailpipe, and header enough to create brittle fracture concerns. Normal operating temperature is not the only material selection basis. Emergency relieving temperature matters. Discharge reaction forces matter too. High velocity flow creates momentum loads and bending moments that can be transmitted into the valve, piping, equipment nozzle, and structural supports. Discharge piping must be independently supported and correctly aligned. The pressure relief valve should never be used as a pipe support. Forced alignment with flange bolts is not alignment, it is stored stress. Thermal movement still matters even if the relief line is normally empty. During an event, the line may become very hot or very cold. The support and flexibility design must prevent that movement from damaging the valve or protected equipment. Drainage is also part of function. Condensate, rainwater, process carryover, cleaning fluids, or leakage can collect in low points. Trapped liquid can create corrosion, freezing, water hammer, added back pressure, and excessive weight. A relief line that cannot drain is not a complete design. Isolation valves create another human system risk. A perfectly sized relief device behind a closed isolation valve provides no protection. Where isolation is required for maintenance, testing, or online switching, the arrangement must ensure that adequate relief capacity always remains available. That may require locked or sealed open valves, interlocks, transfer arrangements, position monitoring, controlled procedures, or full spare relieving capacity. Two valves do not automatically create redundancy. If they share the same vulnerable inlet, outlet, isolation arrangement, or operator error path, they may still have a common failure. Redundancy is not equipment count. Redundancy is functional independence. Finally, installation and maintenance access matter. Relief devices must be reachable, removable, inspectable, and protected from damage. Vent connections must remain open and correctly routed. Heat tracing must prevent freezing or solidification without overheating discs or seals. Insulation must not hide corrosion or leakage. Before installation, verify tag number, set or burst pressure, material, orientation, cleanliness, certification, flange condition, and transport damage. Protect pilot passages and sensing lines from debris. A safety device damaged before startup may remain invisible until the day it is required to save the plant. That is the central lesson of API 520. You begin with the credible scenario, you determine the correct relieving load, you size at actual relieving conditions. You select the device for the real fluid phase, operating ratio, back pressure, temperature, and service quality. You control inlet pressure loss. You engineer the discharge path. You check reaction forces, materials, drainage, vents, isolation, and maintainability. The relief device is only one component in that chain. A correct calculation connected to bad piping is still a bad design. A balanced valve with a blocked vent is still a bad design. A rupture disc with the wrong temperature basis is still a bad design. A pilot-operated valve in fouling service without protection is still a bad design. A redundant arrangement that can be defeated by one valve position is not true redundancy. The final question is not, does the datasheet comply? The final question is, will this complete pressure relief system work when the process is unstable, the header is pressurized, the piping is vibrating, the device has aged, and the plant is depending on it? That is where pressure relief design stops being documentation and becomes engineering accountability. Share your experience in the comments. Have you encountered valve chatter, excessive inlet loss, unexpected back pressure, blocked vents, damaged rupture discs, poor supports, or isolation valve risks on real projects? Challenge the ideas, add your field lessons, and tell me where relief system design most often fails in your industry. Like this episode, share it with engineers who design, review, operate, or maintain pressure systems, and subscribe to the channel for more practical engineering design discussions without unnecessary complexity. Follow my LinkedIn newsletter for deeper articles on engineering design, technical assurance, standards, project execution, and the decisions that separate compliant drawings from reliable plants. For project-specific guidance, technical review, or engineering design discussions, get in touch.